Welcome back to Crazy with Dr. H. I just thought I'd be different today. A little bit more A&P with Dr. H. We're going to be continuing on our cardiovascular journey here. Today, we're going to be talking about the relationship between blood flow, blood pressure, resistance. When we're talking about the heart, hopefully you guys remember that what we're really talking about is the fact that the heart is contracting to push blood out either to the pulmonary circuit or to the systemic circuit. But let's talk about that systemic circuit, right? As we push blood out into the system, we're trying to get blood out to those tissues. In other words, we're trying to create blood flow. And that's what we're going to be discussing here today. Blood flow, now that refers to the movement of blood through a vessel into the tissue or into an organ, whatever the case may be. We normally can think of blood flow and express it in terms of either a volume like mils or volume over time like mils per minute. Now, let's think about this again. Blood flow is initiated by the contraction of the ventricles of the heart. So as the ventricles contract, it's going to push blood out. Let's keep going with this idea. This ventricular contraction is going to eject that blood, right? And where does it go? Into the arteries, into the elastic arteries, into the muscular arteries. So we're creating pressure that is going to push blood from one region to the next region. In other words, we're going from a higher pressure system to a lower pressure system. The further we get from the heart, the lower those pressures become. Now, as those blood vessels branch and branch and branch, right? As they go from being arteries to arterioles, from arterioles into the capillaries, from the capillaries to the venules, and from the venules into the veins, the blood pressure, the pressure gradients are going to be decreasing through this entire time. Cool. Awesome. That's going to allow blood to flow from the left side of the heart all the way back to the right side of the heart. That blood needs to flow downhill that entire time. One last thing to think about in terms of all of this is that what is opposing blood flow? Well, if you're pushing blood through a tube, that tube is always going to be applying something called resistance. And resistance is constantly impeding or slowing blood flow through that system. Cool. That's the background story. Now let's write it out. Let's think about what this all means. All right. Let's use some of the previous information to discuss this current information. So the very first thing that I'm going to talk about is we're going to go back in time and talk about cardiac output. Because cardiac output is, if you think about the story that I just talked about, if we're talking about the ejection of blood that creates blood flow, hopefully what you guys are thinking about is cardiac output. So first and foremost, we can say, hey, cardiac output is going to create that blood flow. So we can say cardiac output is proportional to blood flow. As cardiac output increases, blood flow is going to increase. And actually, I should have had these backwards. I did this in lecture in class too, which is bizarre, right? What we actually want, let's get rid of that because I did that again. My students are going to laugh at me. But blood flow is actually proportional to cardiac output. And this is important because the right side of the equation affects the left side. The left side doesn't affect the right. So that's why that's important to write that out like that. Okay, so what do we know? If the heart beats stronger, what's going to happen to blood flow? It's going to increase. Whereas if the heart beats weaker or slower, then blood flow would decrease. So they're proportional to one another. They do the same thing. So that's just the first thought process. What's determining blood flow? The primary thing that determines blood flow is that the heart is beating. So what's happening as that heart beats? Well, cardiac output is going to start creating pressure. that pressure is highest near the heart and it's lowest as you move away from the heart. So let's go ahead and draw this out. And we could just do a quick little diagram, right, of the left side of the heart, because that's what we're interested in. So we'll have the little left atria and down into the left ventricles that now flows out into the aorta. And now that's just the left side of the heart. Hopefully you guys can see that. That's the left ventricle, left atria. And then we got the aortic semilunar valve here. And blood is going to be getting ejected out of that heart. This, over time, is cardiac output. So what's that going to do to pressure nearest to the heart? It's going to increase pressure. And in fact, if you start looking at the pressure closest to the heart, you'll find that the pressure closest to the heart tends to be what you're measuring when you're measuring somebody's systolic blood pressure. It's about 120 millimeters of mercury. Now, as you move away from the heart, what have we said? Right? As you move away from the heart, that blood pressure is going to decrease, decrease, decrease. By the time you get it out to the tissue level, you're going to be at approximately 35 millimeters of mercury. What's the gradient? Remember, gradient is the difference between two sides. So in this particular scenario, the gradient would be 85 millimeters of mercury, which is a pretty steep decline, right? So blood's going to flow from this area all the way to this area because it's constantly going down its gradient. So we're having a decrease in pressure relative to close to the heart, FYI. In other words, that cardiac output that's pushing blood out is going to create a pressure that runs down its pressure gradient, and we could write this out as delta P. Okay, delta in math, that means change. So this is a delta P. There's the gradient or pressure gradient. So what do we know? We can exchange cardiac output for delta P. So blood flow now we can write out as proportional to delta P, where delta P is determined by that cardiac output. Awesome. What would happen if delta P, right? This is just a thought, hypothetical. What would happen if the pressure over here was 120 millimeters? What would delta P equal? If on the right-hand side we had 120 millimeters, then 120 millimeters minus 120 millimeters, that delta P would be 0. What do we know about blood flow in that scenario? When the pressures on two sides of a tube are equal, there is no blood flow. So that's a kind of an interesting idea. Now, blood flow just would equal 0. Awesome. But what else do we know about blood vessels is that blood vessels branch and diverge. And as they branch and diverge, they get smaller and smaller and smaller. And they're also surrounded by smooth muscle. And that smooth muscle, by the time we get way out here at the tissue level, right, we're going to end up with arterioles. And those arterioles are going to feed into the meta-arterioles. And we're going to have our capillary beds. So hopefully this is just a reminder to y'all, right? We don't want to overcomplicate this drawing. But here's that capillary bed. So we keep getting smaller and smaller and smaller, and we have lots and lots of smooth muscle out here. And what we're able to do as things get smaller is that's going to start to oppose or interfere with the movement of blood through that tissue. So that's going to start to decrease blood flow through that tissue. And we'll see how that comes back into play. Okay, this is called resistance, which is what we have up here in the title. And if you think back to my introductory paragraph, I also talked about this opposition of blood flow. So if we're opposing blood flow, what we want to write this out as is that blood flow is inversely proportional, or blood flow is proportional to 1 over that resistance. Okay, so blood flow is proportional to delta P, directly proportional, but it's inversely proportional to resistance. And we just talked about one way that resistance can be created in the human body, but there are actually many ways. So we're going to write that in. We're going to say where resistance, that's this capital R, that's resistance. But when we talk about resistance, resistance is actually equal to something called, I can't pronounce it. I think it's French, right? Poiseuille's equation. And Poiseuille's, Poiseuille's, who knows? I don't know. My professors taught me once upon a time, and then I got through the rest of my PhD without actually ever having to go through the actual name. But what this is basically it's an equation that starts to define resistance. And we'll see how it adds back into the total blood flow in just a minute. But resistance has three major factors that affect it. Okay, the first major factor is the length of the tube, and it's actually 8 times the length of that tube. The second major factor that affects it is viscosity, or the thickness of that fluid, and we write that out with a Greek letter nu. All of this is going to be opposed by the diameter of that tube, and in Poiseuille's law, we end up writing this out as pi 3.14, right? Lowercase r, which equals radius to the 4th power. This is a very important equation that describes resistance through a tube. Okay, where we'll go ahead and write this out, where the 8L is equal to the length, where the nu, I'm going to want a little bit more room here, but I'll make this work, is equal to the viscosity, which is the thickness of that fluid. And last but not least, actually the most important, is r, lowercase r, equals radius. Let's think about each one of these variables, such as length, the length of your blood vessels. Well, length of the blood vessels changes rapidly as you're growing, of course, right? As you're going from toddler to small child, all the way to adolescence, all the way to adult, you're growing, and as you grow, your tissues need more blood vessels. So the length of your blood vessels is increasing through this entire time. Now, when you're an adult, you've hopefully stopped growing too much, but you can still grow, unfortunately, typically in girth or in muscle. So as you gain size, mass, whatever the case may be, that's going to end up resulting in more blood vessels. We're going to come back to some numbers that relate back to this, but let's go ahead and think about some potential pathos, or just potential things to think about in a patient in terms of resistance and how length is going to affect that resistance. So let's go up here and say, what would happen if somebody was taller? Doesn't it make sense that the height of a patient is going to determine the length of their blood vessels? The taller they are, the more mass they have, the more the distance that this blood is having to travel. And so if I got a longer distance, what's going to happen to the resistance? It's going to increase. So a taller patient, someone that's 7 feet, for instance, their heart is going to have to work harder to get that blood to the tissues. Something to think about. Something else to think about is the weight of that patient. Now, this isn't going to have a huge impact on your patient, but it definitely can, where adipose tissue requires blood vessels. Granted, not a massive amount of blood vessels, but it still requires blood vessels. In fact, about 1 pound of adipose tissue contains about 200 miles of blood vessels. That's pretty impressive, in my opinion. And I think that's really, really, really cool. If you think about the math of that, if you gain about 10 pounds of fat, that's about 2,000 miles of new blood vessels. Now, relative to total number or miles of blood vessels in the body, your about a 150-pound patient, they have about 60,000 miles of blood vessels in their body. 60,000. So 2,000 isn't a huge addition to the 60,000, but it does end up making an impact on that resistance. So height and weight can affect the length, but in a normal, healthy person, not as much. And we'll also put in growth here just so you guys can think about that. Viscosity. There are two major factors that affect viscosity. The number one reason for viscosity in the blood, hopefully this takes you back to your lessons on blood and the components of the blood cells, right? So viscosity is going to be controlled by cellular components or formed elements. And the number one formed element that controls viscosity are erythrocytes, right? So we want to think about these red blood cells, erythrocytes. So erythrocytes, normally we don't change these in a massive degree if we're healthy, but a patient could potentially have polycythemia, right? So what's going to happen to the viscosity of a patient with an increased production of red blood cells? Right? Somebody has polycythemia, more red blood cells, the viscosity goes up. As the viscosity goes up, right, we come over to this equation, as the viscosity goes up, resistance is going to go up. What about a patient with anemia? Right? Typically anemia, especially if it's an erythrocyte related, anemia is going to end up decreasing the viscosity. If you decrease the viscosity, you decrease that resistance. What about if somebody has polydipsia and they're drinking too much water? So now we can start to think about fluid itself being a major determinant of viscosity. Now, water is going to lose the viscosity of that blood. It's going to make it so it's less thick. So somebody starts having polydipsia and they drink too much water, then the viscosity is going to decrease, thus reducing the resistance in that system. All right, the last part of this is the radius, right? This is actually the most important factor, and that's indicated by this fourth power. Pi, well, that's constant, so we don't really need to worry about pi at all. We can actually ignore it in terms of this equation. But radius is going to be determined by, well, two major things that control it acutely in a healthy patient. By the way, this is going to be the number one factor in a healthy patient that is going to regulate blood flow. By far the most important factor for you guys to focus on is the radius. Because in a normal healthy person, we could either vasoconstrict or we can vasodilate. So let's put that into our equation over here. If we vasoconstrict, what happens to the radius? Vasoconstriction makes the radius smaller. So as the radius decreases, well, it's inversely proportional to the resistance. So as the radius decreases, the resistance increases. We'll tie that back into blood flow in just a minute. Versus vasodilation, now the radius increases, so the resistance decreases. Are there some other things disease-wise that can affect the radius of the tubes? Absolutely. Right? We can have an embolism, atherosclerosis. We can have a decrease in the compliance of a artery, make it stiffer so it can't expand as well. And that's going to make it so that the blood doesn't flow through it quite as well because we can't regulate that radius. All of these is going to impact the bottom of our resistance, right? So it's going to have a opposite effect on the resistance. I think that's pretty darn cool. I think that's pretty darn cool. So again, let's start looking at these things. What if we were to increase the height? Let's go back over here. If we increase the height of a patient, what variable is affected? The length. Therefore, what happens to resistance? It will increase. Awesome. Let's go and just pick one at random down here. Let's go ahead and say, I like polydipsia. So let's go ahead and say polydipsia increases. Well, an increase in water content is going to decrease viscosity of the blood. And if you decrease the viscosity of the blood, what happens to resistance? It will decrease because it's directly proportional to that viscosity. Now, last one but not least, obviously, actually the most important of these factors is R to the fourth. And we'll draw out what the fourth means in just a second. But let's go ahead and vasoconstrict. So if we increase vasoconstriction, what happens to the radius? As you increase vasoconstriction, you decrease the radius. Remember, it makes the tube smaller. And as you decrease that radius, what happens to the resistance? It will increase. Why is the radius the most important factor? I guess, how does this equation prove that radius is the most important factor? It has to do with this power. So just real quick, and I always do this with my students. I know not everybody loves math, but it's helpful. Is that if radius equals 1 centimeter, then what is R to the fourth, right? If radius equals 1 centimeter, well, then we have 1 times 1 times 1 times 1. So that is going to equal 1. Remains 1 centimeter. But let's increase the radius twofold. Let's make this 2 centimeters. So now what do we know? When we increase this twofold, now radius is going to be 2 times 2 times 2 times 2. So that's going to have an impact of 16. Really, it's a fold change. We really shouldn't put these units in here, not on this side, right? So this is going to end up creating a 16-fold change in resistance. When all we did was double the radius, we created a 16-fold change in resistance. Huge amount of power. Powers represent power, literally. Cool. Let's go back to this now. What we said was that if a patient gets taller, the length gets longer, the resistance goes up. But what do we know about resistance? As resistance increases, it's inversely proportional to the blood flow. So what's going to happen to blood flow through that 7-foot patient? Blood flow is going to decrease. It's going to be harder. Their heart is going to have to work harder to get blood flow back to normal. What about if a patient has polydipsia and they're drinking too much water? We know viscosity is decreasing. Therefore, resistance decreases. But as resistance decreases, what's going to happen to overall blood flow out to the tissues? We're going to actually get too much blood flow, and this is going to create overperfusion of that tissue. What about the radius down here? If we vasoconstrict, then the radius decreases, and as the radius decreases, the resistance increases, and as the resistance increases, blood flow to that tissue will decrease. And that's how you use this equation, y'all. If you understand this equation and how these equations interact, you can actually look at all sorts of diseases. As long as you know that particular disease affects the length, or that particular disease affects viscosity, or causes hypertension or something along those lines and changes the radius of the tubes, boom, boom, we can get right back to what's happening to blood flow to those tissues. And blood flow is critical. It feeds that tissue with oxygen. It feeds that tissue with nutrients. You got to have it. So as we start to change blood flow, say for instance, decrease blood flow, we get less oxygen, we get less nutrients. But we got issues if we overperfuse that. If blood flow gets too high, then it's going to actually cause edema in those tissues, or it can end up causing vascular damage because the pressures are going to be too high. Let's tie these ideas together now. We haven't done it completely. It gets even, I think, easier when we start to tie everything together. So if we know blood flow is proportional to delta P, but we know blood flow is inversely proportional to resistance, then we can say, well, blood flow is simply proportional to delta P over resistance. And since we know resistance is equal to 1 over r to the fourth, that is going to be the most important part of this. The length, healthy patient, don't worry about it. The viscosity, healthy patient, don't worry about it. Pi, don't worry about it. It's 3.14. So the most important thing that happens out of this is 1 over r to the fourth, and we can actually take and represent that over here. Now, if you want to now get this, because you can't have delta P is over 1 over r to the fourth. So we need to flip all of this around, if you remember your pre-algebra here. So if we wanted to write this out, we can actually just say blood flow is proportional to delta P times r to the fourth. This kind of comes out much easier to try to understand. And then, of course, if you wanted to add the rest of Poiseuille's equation in here, we would end up saying this is divided by length times viscosity. Ends up complicating the system, but in a diseased patient, we need to think about those things. So what do we see here? If vasoconstriction occurs and the radius decreases, well, we went through this big long process up here where radius decreased, therefore resistance increases, and since resistance increases, it's inversely proportional to blood flow, therefore blood flow decreases. But now we have a nice simplified equation that in a normal healthy patient we can use. When we're just thinking physiology, we can use vasoconstriction decreases the radius, and therefore what happens to that blood flow? They're directly proportional, therefore it decreases that blood flow. So it's really helpful in understanding that context. Cool. What else can we get out of this? Pressure. Okay, pressure. We said pressure is determined by cardiac output, but it's not going to be the only thing that controls pressure. So let's pull this pressure out and start saying something else about it. Okay, we know that this pressure gradient is actually going to be created by mean arterial blood pressure. Mean arterial blood pressure. Mean arterial blood pressure is therefore going to help control delta P, and delta P is going to help control mean arterial blood pressure. And actually, we should go a little bit. I did what I did up there. Whatever. Bad at that, huh? Don't think about it until after I write it. Delta P is going to be proportional to MAP. So MAP is going to help control this delta P. So what exactly is MAP? We got to keep going. Sorry. Right? This is mean arterial blood pressure. That's what we're dealing with, mean arterial pressures. So this is the pressure inside of the blood pressure, but as a mean. Because if you measure a patient's blood pressure, you're going to end up with something like 120 systolic blood pressure, so millimeters of mercury, over approximately 80 millimeters of mercury. But what does that mean, right? This is systolic, and the bottom value is diastolic. Hopefully you guys have learned this already. If not, well, surprise. Right? Systolic and diastolic blood pressures. So your blood is seeing a range of blood pressures. 120 at max, 80 at minimum is what that means. So mean arterial blood pressure says, where does the blood vessel normally stay at? What blood pressure does the blood vessel normally stay at, which is going to create the pressure gradient that is going to drive this down to the tissues. Right? So in order to look at MAP, we need some variables to come out of this. First, we're going to need to measure the range of pressures that that patient's blood vessel sees. Okay, the range. So what is 120 to 80 in essence is what it's saying. And this is called pulse pressure. Pulse pressure is also written out as just PP, which makes, of course, everybody giggle. So PP. PP, or the pulse pressure, is now equal to the maximum pressure in the heart minus the minimum pressure. So it's systolic blood pressure minus diastolic blood pressure. That's our pulse pressure. So in a normal patient, we'd have 120 millimeters minus 80 millimeters of mercury, right? 120 millimeters of mercury minus 80 millimeters of mercury. So that normal pulse pressure would be about 40 millimeters of mercury. Cool. Well, that doesn't tell us as much as we'd like it to tell us. In fact, in order to measure mean arterial blood pressure, we need more than that. We're going to actually want to add that value back to the minimum blood pressure because we know that our mean arterial blood pressure has to be above 80 millimeters of mercury. I shouldn't have written it in as that. Diastolic blood pressure. We know that our mean arterial blood pressure has to be above the minimum value because it's somewhere in between 120 and 80. So we're going to take our diastolic blood pressure, which is 80 millimeters of mercury, and we're going to add something back to it. In fact, we're going to add back parts of the pulse pressure. But what did we find out pulse pressure is? It's systolic blood pressure minus diastolic blood pressure. So that would be 40 millimeters of mercury. We don't want to add 40 millimeters of mercury back to 80 because that would just get us back to 120 millimeters of mercury. We know that it doesn't stay at 120 millimeters of mercury all the time. Mean arterial blood pressure is somewhere in between. The last part of this variable I find is the one that's not explained at all in most textbooks, and a lot of the other YouTubers don't explain it at all, is they just write down this value. They say, okay, take diastolic blood pressure and add back 1/3 of the pulse pressure. What the hell does that mean? That's how I learn, is you got to understand what it means in order to actually use it on a daily basis. Where's that 1/3 coming from? What this 1/3 is coming from is the cardiac cycle. Okay, so when we look at a cardiac cycle is comprised of systole and diastole. And that systole here is the contraction of the heart, and the diastole is the relaxation of the heart. But how much of the cardiac cycle is made up of systole? When you look at the entire cardiac cycle, what you're going to see is most of the cardiac cycle is the heart relaxing, refilling with blood, and only a small portion of systole is the heart contracting. In fact, on average, systole is only about 1/3 of your cardiac cycle versus diastole, which is about the 2/3 that are left over of your cardiac cycle. So where does this 1/3 come from? It's coming from the fact that the heart's only contracting for about 1/3 of that cardiac cycle. So most of the time, your blood pressure is going to hang out near diastolic blood pressure. 2/3 of your time, it's going to be down by the diastolic blood pressure, but only 1/3 of the time is it going to be up towards the systolic range. So on average, it spends more time closer to 80 millimeters of mercury. So that's why we add back 1/3. So if you do the math on this, right, we can say in a normal patient, MAP is going to be 80 millimeters of mercury plus 1/3 of the pulse pressure, which is 40 millimeters of mercury. Or in other words, 80 plus 13.333333 bar. But we don't want to do that, right? we just average that, we round down. So the normal blood pressure, the normal mean arterial blood pressure across the United States and across the world, as far as we know, is approximately, right? This is just average, 93 millimeters of mercury. And that's what that math all comes out to. Oh, Dr. H, do we really need to know all of this math? The answer is yes and no, because there's something else to think about here that we can actually use, similar to what we used up here with blood flow. Okay, and that is that there are a bunch of determining factors that control your mean arterial blood pressure. Okay, and I always just talk it out. So mean arterial blood pressure, and this is where we're going to end this particular lecture, and then in the next lecture we'll dive back into mean arterial blood pressure and the intrinsic and extrinsic controls of that mean arterial blood pressure. Right? So blood flow, we've talked about it. Resistance, we've talked about it. Blood pressure, we started talking about it. Let's finish this off. And we can use our equation over here to help us. And all of these times that we said things are proportional to help us. So we know that pressure gradients help regulate mean arterial blood pressure. We can just insert that into the equation. So we can say, well, blood flow is cardiac output. And this is weird. And what else do we have going on? We have resistance. And really what we're interested in is all of the resistance that's going on throughout the entire body, all systemic, all peripheral resistance. And we end up calling this T, total, P, peripheral resistance, total peripheral resistance. So let's solve for MAP. And what you'll end up seeing here is that MAP has two major factors that affect it. To start, we're going to add another one to it. But this is now going to be cardiac output, which, yeah, you got to know. The resistance, the total peripheral resistance, that came out of this equation right here. So this is one that we want to use. Now, there's another factor that I find really important to write into my MAP equations. Again, not all professors do it and not all YouTubers do it. I think it's critical because it acts separately compared to cardiac output and TPR, and that is your blood volume. Okay, I think blood volume is very important to discuss separately. So ultimately, when you guys are going to talk about blood pressure, I hope you guys end up writing this here equation down, where, we'll go ahead and finish it off like this, where cardiac output equals heart rate times stroke volume, where resistance or total peripheral resistance, well, that's just the resistance we talked about up here, right? So this is going to be the whole length times viscosity all divided by pi r squared. 8 times the length times the viscosity all divided by pi r. I said squared, but to the fourth. And last is blood volume. And something I like to write down and think about in my head all the time is, how is blood volume affecting everything? Well, I think sometimes it's nice to think about it opposite than that. I like to think about blood volume as how much you're drinking or how much a patient's bleeding out. Where is the blood actually going at any given time? And one important thing that we're going to talk about, especially when we get to the urinary system, okay, is that blood volume, it's got to come from somewhere. And if blood volume is too high, what's going to end up happening is that a patient's going to end up peeing that blood volume out. Or if a patient's not peeing enough, then the blood volume starts to increase. So in other words, blood volume is inversely proportional to urine volume. As urine volume goes up, blood volume goes down. And as urine volume goes down, blood volume goes up. Each one of these variables is going to come back to play a role in the next lecture when we talk about the intrinsic and extrinsic controls of mean arterial blood pressure. Because what do you know your body can now do? If blood pressure gets too high, what's the body going to try to do? We're dealing with physiology here, peeps. So if blood pressure gets too high, then the body's going to try to bring it back down. Homeostasis. Go ahead and write an exclamation point here. You got to remember homeostasis. So what are the major things the body can do to maintain homeostasis on your mean arterial blood pressure? Okay, blood pressure gets too high, we're going to try to bring it back down. Can we decrease cardiac output? Heck yeah, we can. What can a patient do to their heart rate? Drop it. What can they do to the stroke volume? Drop it. They're going to inhibit the sympathetic nervous system to do that. What about total peripheral resistance? Can we alter resistance? Yes, we can. What's the most important variable that controls resistance? Just drop my pen. That controls resistance right here, right now. That's that radius. So what are we going to do? Are we going to vasoconstrict or are we going to vasodilate? To bring mean arterial blood pressure back down, we vasodilate, and that brings resistance down. So total peripheral resistance can decrease to drop that map back down. And what about blood volume? Can we change blood volume? We sure can. How can we do that? We can change urine volume. So a patient now that has a map that's too high, are they going to pee more or are they going to pee less? They're going to pee more, right? There's a lot of hormones that are involved in that process. And we're going to talk about atrial natriuretic peptide to bring blood pressure back down, or renin, angiotensinogen, angiotensin, right? Ang1, Ang2, aldosterone, and ADH, which are all going to try to bring blood pressure back up if MAP gets too low. We'll talk about that in the next lecture. So, hopefully you found today's lecture useful. It was a relative actual crash course here. It happened really fast. Even though it's 42 minutes in, this is a lot of material to absorb. So please think back through this material. Make sure you can write down these major equations. Write down these major equations, which I summarized down here, and understand each variable that impacts that equation. And what would happen if you changed one of those variables? That's what your professors should be asking you about. Hopefully, that's what you guys see on your exams. All right, this is Dr. H. All done here. See you in the next video. Humankind, you know what I'm going to say, right? Humankind, be both.